Lesson 4. So, good morning, students. I'll send you one PDF in which some notes were there. Let us now discuss those questions. Define electrical field intensity and give unit. You see, electrical field intensity is represented by the letter E, and you will soon learn that it is a vector quantity. The unit of electrical field is Newton per coulomb, and the other unit is volt per meter. Shortly, we will be able to see why the units are like this. Firstly, let us try and define what do we mean by electrical field intensity at a point. The electrical field intensity at a point P due to a charge Q has been defined as the force experienced by a unit positive charge when placed at that point P. So whatever is the direction of that force experienced by unit positive charge at the point P, that would be the direction of the electrical field lines. Now, common sense tells us that if I keep a positive charge over here, then due to this positive charge, there is going to be a force of repulsion, and therefore E vector should point away from the charge. If I have a negative charge, capital Q, and I keep a unit positive charge at P, then there will be a force of attraction, so the electrical field will point towards the charge. What we are learning out of this is very simple, that due to a positive charge, the electrical field will point away from it, and due to a negative charge, the electrical field will point towards it. That's what we have to learn. So here, due to the positive charge, is shown that the electrical field is going away, and due to the negative charge is showing that electrical field is coming towards it. We defined the electrical field, and we said that this is the force experienced by a unit positive charge when placed at that point. It's very difficult to find a unit positive charge. So what we do is we take a test charge Q0 over here, and we try to evaluate what is the force experienced by this charge Q0. So F divided by Q0 will mean the force acting on a unit positive charge. Anyway, what we're learning is that E is equal to F divided by Q0. This expression is now written like this, that vector E is equal to limit Q0 tending to 0, F divided by Q0. Limit Q0 tending to 0 implies that the test charge is vanishingly small, so small that it may not disturb the other charges placed near it. So the test charge Q0 that we are talking about must be very, very small, and in stylish language we can call it as that it is a vanishingly small test charge. Now we start with the second question, which is express the electrical field intensity due to a charge in two different forms, in the general form and number 2 in the vector form. So here you see we have expressed the electrical field in the general form. If you have a charge Q, then the electrical field intensity at the point P is simply kq divided by r square. You may wonder why it should be like this. You may say that you kept a unit positive charge at the point P, so let me find the force. Force would be k capital Q into 1 divided by r square. Anyway, general formula is simply E is equal to kq upon square of the distance between the charge and the point. Now let us see how we could express this in the vector form. Here we have taken a point P with position vector r0, and I've taken a charge over here as capital Q, which was not mentioned here, charge capital Q with position vector r1. Now we have to learn a rule. A vector will always be final position vector minus initial position vector. So this vector that I've drawn, this is by the rule that a vector is always equal to what? Final position vector minus initial position vector. So we write the formula for the electrical field in the vector form like this: kq into r0 minus r1 vector divided by r0 minus r1 ka whole cube. You would say that this is the same formula which we learnt in the Coulomb's law. The only difference is that one is missing over here. Otherwise, the formula is the same. So kq into r0 minus r1 divided by r0 minus r1 ka whole cube. Imagine if you have a charge, another charge number 2, then in that case, the formula would be k multiplied by that charge multiplied by r0 minus r2 divided by r0 minus r2 ka whole cube. So this we have to commit to memory. The last in this is to draw the variation of electrical field with distance. The formula for electrical field was kq upon r square. So E will be inversely proportional to r square. You have seen this earlier in the case of force. This is simply inverse square law. And anything which is inversely proportional to r squared, the graph you know would be like this. And you've heard this word called rectangular hyperbola. So that's how we draw the graph between electrical field and the distance. Now we are starting with the next very important question, namely, what are electrical field lines, and state some important properties. So electrical field lines are either straight lines or curved lines such that tangent at any point to the curve gives the direction of the electrical field at that point. Now we begin with the second part in this. What are the properties of electrical field lines? These properties are very important in order to answer the reasoning questions. The first property tells us that they start from the positive charge and they terminate at the negative charge. So in the exam we will be asked why electrical field lines cannot form closed loops. Our answer is simple: because E lines, they start from the positive charge and they terminate at the negative charge. Second, these are smooth continuous lines. Now how do we know why should electrical field lines be smooth and continuous lines? Because the electrical field around a charge exists at each and every point. That means E lines cannot have any abrupt change in the direction of the electrical field. The third, this is very famous: no two electrical field lines can ever intersect each other, simply because at the point of intersection, then it would mean that there are two different directions of the electrical field at a point. Now since this is impossible, therefore E lines can never intersect each other. The last, they are always perpendicular to the surface of a charged conductor. So in the exam they will ask, why should the electrical field lines be always perpendicular to the surface of a charged conductor? The answer is that if the electrical field lines were to have a component along the direction, along the surface of the conductor, then it would cause movement of the charges from one point to another. It is for that reason that E lines will always be perpendicular to the surface of the charged conductor, because if they have a component, then in that case it will cause movement of the charges. Since that is not possible, therefore E lines must be perpendicular. The last point which I have not mentioned here is that the electrical field inside a conductor is always 0. Very soon you will learn in Gauss's theorem that this fact we call as electrostatic shielding, meaning the electrical field lines inside a conductor is always 0. In other words, there are no electrical field lines inside the conductor.